Our next chapter is computer hardware. In this chapter, this is chapter 3 of the book that is used in O levels computer science. Let's start that. The first topic is computer architecture. Let's see the introduction. CPU controls and processes all the instructions. Performance depends on several internal factors. Modern CPUs are designed for speed and efficiency. There's some hardware used in computer science. Basically, what happens in our computer science, if we open our computer, there is a motherboard on it, and motherboard has uh, different components that are connected to it. CPU is one of the most important, that is considered as the brain of the computer. So in CPU, there are other components of the CPU that make it usable for us and beneficial for us. Let's see what are those components. The purpose of CPU is that it processes all the instructions and overall working of our computer, and it is designed. They are designed for the speed and efficiency. Let's see the main components for CPU. CPU has main components: control unit, arithmetic logic unit, registers are the memory unit, and they are buses. Let's talk about the arithmetic logic unit first. ALU is used for plus, minus, divide, multiply, all those operations. They are logical operations like AND OR that return the value true, false, like stuff. So they are used for those. There are other shifting operations and multiplication and division. There are numerous operations that are used in binary or in the mathematics. So all of them are performed by arithmetic logic unit. Let's see and look at this diagram. This is a diagram of the CPU, and there are buses that connect all those components to the external components of the CPU. External components that are on the motherboard like RAM, or this diagram is entirely of belongs to CPU, and there are buses connected to it. So let's see. First, let's look at from the left to right. They are arithmetic logic unit and control unit, and there is a system clock. System clock is directly connected to the control unit, because control unit and you should just for now, for the sake of argument, just think that these are almost the same thing. Control unit and system clock, they basically work together. There's arithmetic logic units. So these are our main core units. Next are our uh, memory units. Those are our address registers. So memory units are memory address register. They all registers have different purpose. Program counter is also a register. CIR is a register. Current instruction register. Accumulator is a register, and memory data registers. MDR is another register for data. And you can see they are connected to the buses, and buses are going outside the CPU, because buses connect CPU to the external components like RAM, hard disk, and other stuff. Let's move on. Now let's talk about the control unit. It controls all operations of the CPU, fetches and decodes the instructions, send signals via control bus. Let's say what happens, we have some instruction comes, and control unit makes a decision that which instruction could to execute, and all uh, it fetches and decodes the instructions. What it does, basically the instructions that are present in the current instruction register, CPU does, it fetches and decodes that instruction, and uh, that is sent to the relevant place. If it has its arithmetic logic instruction, then it is sent to the ALU, and it sends signal via control bus. Through control buses, all the signals are sent all around the computer. Uses system clock for synchronization. It uses system clock for managing time between the different instructions. And role of RAM. RAM stores data and programs needed by the CPU. Also, it is also called immediate access store. Data is moved from hard disk to RAM. Because RAM is much faster, it takes less time in read-write operations. RAM equal to fast workspace. Hard disk equal to slow storage. So result, faster computer performance. So RAM is faster than hard disk, so the computer performance is faster with better RAM. And then there are registers. They are fast memory inside. They are present inside the CPU. Program counter holds the address of the next instruction, And memory address register stores the address of the instruction that is gonna be executed, and then the memdr stores the data or instruction, whatever it is. And the current instruction register, the cu basically decode picks the data or instruction from the current instruction register to uh, decode it and execute the instruction by the CPU. Then accumulator stores the results of the calculation. Any result that is performed by ALU or CU, that is stored in the accumulator. Let's see. Memory is made of many locations. Each location has address, data contents like and stored in binary, and the address is a unique identifier. Example uses 8-bit address plus 8-bit data. Real systems use larger sizes. Of course, this is just a random example, not for the real world system, but real world system has better address like 32-bit or 64-bit address. Read operation address, step 1. Let's see, we have a address uh, 4 ones and 0001. It is loaded into the memory address register. Then read signal is sent to the memory. This is the example of the read operation. How is it happening? This is the binary address and it is loaded into memory address register. Once it is loaded into memory address register, read signal is sent to the RAM, and then data at the address is loaded into the MDR, and then the MDR has some data. That's you can say this is the data because everything is in binary, so you can say this is address, this is data. And then there is a write operation. Data this data is loaded into the MDR, and then address loaded into the memory address register, and then write signal is sent. Once the write signal is sent, data is stored at the memory location, you can say in the RAM, and then memory address register holds the address, memory data register holds the data, and input output devices enter data. Output devices display the results and they get that result from the accumulator. Let's say von Neumann architecture, it work. This is the computer's architecture that is used in the modern computers. And von Neumann architecture, what it does, it uses stored program concept. CPU accesses memory directly like RAM and stores both data and instructions. Instructions executed sequentially because system clock works in a way that instructions are executed in a sequence. Then system buses, address bus, there is a it carries the addresses, and wider bus, it carries more memory addresses. Then there is a data bus, it carries data both directions, transfers in instructions and values. And then there is a control bus, it carries signals and manages operations of the components. Then there is a fetch decode execute cycle. uh, how to fetch address is fetched from the program counter as it holds the address of the next instruction, and then instruction is fetched to MDR, and then it is moved to CIR, and program counter is incremented, and CU decodes the instruction by picking it from the CIR, and then execution is carried out by the CPU. Okay, let's do the buses, and then I will be explaining you this whole architecture with the diagram, the initial diagram that we saw. Buses are parallel wires used to transfer data in a computer. Each wire carries one bit. It is used in von Neumann architecture. Three main buses: address bus, it carries memory addresses. It is unidirectional. CPU CPU memory direction only unidirectional, and wider bus equal to more memory that memory locations can be accessed. 16-bit it means that many locations. 32-bit means that many locations. 4 plus billion. Data bus carries data, works in both directions. Wider bus equal to larger word size and better performance. Okay, next is control bus, carries control signals and between CPU and other components, and usually about 8 bits wide. No need to be very wide. Okay, let's talk about the diagram first, that how system works. I'm going back to the CPU diagram. This is the diagram. This is a very important diagram. Okay, now suppose we have two instructions. Let me write it down here. You can say this is I1 and you can say this is I2, second instruction. Each instruction has the address. You can say address is A, the instruction of second is I2 is address is B. Now these instructions are loaded into the memory, and one instruction that has to be executed. So its address that has to be executed next. That address of that instruction is in the program counter. Imagine our computer is already executing current instruction. It already has CIR current instruction in the current instruction register. What is happening? So program counter is pointing to the next instruction. Imagine current instruction is I0. This is the I0. Wait, this is I0 is the current instruction that is present in the current instruction register. This instruction is here. So what is happening? Once the instruction is here, program counter is incremented means now the program counter has the next instruction that is I1. Program counter has the instruction of the address of the next instruction. It has the address A, and current instruction register has the instruction 0. It has some address. You can say it has some O address, any address you can imagine. So this instruction is being decoded by the control unit, and then arithmetic logic unit performs that operation and sends the result to accumulator, and then from accumulator the result is sent to the any output device. So this is how the instruction is happening. Instruction is fetched, and then CU is decoding the instruction, and then CPU is executing the instruction by using arithmetic logic unit and accumulator, and the result is going to the output devices. This is how the whole execution process is occurring. Now the program counter has the address of the next instruction, that is I1, and it has the address A. Now the address A is going to be loaded to memory address register. Once memory address register has the address, this means it now the read signal will go to the memory that is called RAM, and it will get the instruction and populate it that instruction in the memory data register through data bus. Now MDR it has to execute this instruction or data, and it is taken by the CIR. Once it is taken by the CIR, program counter is incremented, and it is has the instruction now address of the next instruction B, and the CU is executing this instruction or data, and this is how the whole process is working. Let's move forward quickly back. You can see this is how the read signal happened. Address and then read signal sent to memory. Data that at that address is loaded into MTR, and this is how we did. Now we do the write operation. Data is loaded into the MDR. Once the data is loaded into the MDR, it has to go to the output device, and the address is loaded into the MAR. Then the write signal is sent. So what happens next? Data stored at that memory location. What happens then? The data is written into the memory. Once it is now it is writing data from CPU to the memory. How? MDR is the data, and data is given through, you can say, some input output devices. MDR has the data, and that data and then the address of that data is loaded into the memory address register, and then it is write signal is sent and data stored in some address of the memory address register holds the address, memory data register holds the data, input and output devices, and they enter the data. How we write? We use a keyboard, mouse, or other input devices to write data into our memory. How we write the data? First, that our data goes to the CPU, then the address is set, and then that write signal is sent, and data is stored in the memory location. Now, von Neumann architecture, we have already studied that. These are our buses, and uh, This is our fetch decode execute cycle. Program counter to memory address is a set instruction fetch to MTR and then move to CIR and program counter incremented once anything is moved to CIR. Then there are system buses. We have already studied that. Let's move on. And then wider bus equal to larger word size. Word basically is the amount of data that CPU can process, minimum amount of data that our computer can process. And then there's a control bus. It carries control signals like read write control signals between CPU and other components. It moves in both directions, like from CPU to components and components to CPU. Address bus moves in only one direction. Next is what we have. We have other cores and caches and internal clock. We will do that later in the next class. Let's keep it here simple and here for now. Thank you.